How do you tune and optimize an AMD Ryzen CPU to extract max performance? In this video, we are going to find out. My name is Matt, I'm a former rocket scientist, and my goal is to help you make the right component choices and put them together the right way every single time. In the It's Not Rocket Science series, we've been helping you troubleshoot and optimize your system to keep your PC running like a pro. It's not rocket science, and as you'll see throughout this series, it really is Lego. In this video, our focus will be on how to properly tune and optimize an AM5 based Ryzen CPU, something every AMD PC gamer and enthusiast should know how to do. I'm sure that many of you have heard about the amazing benefits of undervolting and overclocking your CPU, but either don't know how to do it or are scared of messing something up. For AMD Ryzen CPUs, it's actually quite easy to do. However, if you push your system too far, it might not boot, or if it does, you might get system errors. But don't worry, in this video, I'll provide you with a step-by-step guide on how to tune your CPU the right way, allowing you to lower your temps and increase performance without impacting stability. The test system that I'm using for this video is my AMD AM5 open bench table with the following components. For the CPU, we have an AMD Ryzen 9 9950X3D. For the motherboard, we have an ASUS ROG Crosshair X870E Hero. For RAM, we have G.Skill Trident Z5 Royal Neo RGB 32GB of DDR5 8000 at CL38. For the GPU, we have an ASUS ROG Astral GeForce RTX 5090 OC Edition. For the CPU cooler, we have an ASUS ROG Ryo 3 360mm AIO. For storage, we have a 4TB Samsung 990 Pro NVMe Gen 4 M.2 SSD. And for the PSU, we have a Corsair HX 1200i Platinum 1200W power supply. Affiliate links for all of these components are listed in the description below. You can tune and optimize an AMD AM5 Ryzen CPU different ways and with different tools. The process that I'll walk you through in this video is a robust approach that I've developed and modified over a long period of time to not only ensure that you achieve maximum performance, but also that your system remains stable. Given that the PBO feature set that I'll be using in this guide was developed by AMD, the risks are minimal, so it's something I would encourage you to try. One important point to understand before attempting to tune your CPU is that your results will vary based on the quality of your silicon. Some people will get lucky and get a golden sample chip that can undervolt and overclock extremely well, and some will get unlucky and see very minor results. This is called the silicon lottery, because the silicon quality you get when buying a CPU or GPU is effectively a roll of the dice. That said, you'll never know unless you give it a shot. Before tuning any component, you should first check the stability of your system at stock settings, and then benchmark it to establish a baseline. Since this is a CPU, I typically use Cinebench R24 and 3D Mark CPU Profile as my primary benchmarking tools. You can choose any tool you like, including games, as long as it heavily loads your CPU. A mistake I see people make, including larger tech YouTubers, is that they will often use a GPU benchmark, such as Steel Nomad, to test a CPU, which makes absolutely no sense. Once you've established a baseline and recorded your benchmark scores, you can then start tuning your system. When you overclock your RAM in BIOS, you're presented with multiple profiles. The most common profiles are Expo 1 and Expo 2, with motherboard manufacturers adding custom options such as Expo Tweaked. If you're using an XMP RAM kit with an ASUS AMD motherboard, these profiles will be listed as DOCP or Direct Overclock Profile. So which option is best? The most stable profile will typically be Expo 2, since this will apply settings programmed from the RAM kit manufacturer and therefore should work on any motherboard. However, since this profile has not been tuned for your motherboard, it will result in the lowest performance boost. Expo 1 is, however, a profile developed by your motherboard manufacturer and includes performance-enhancing tweaks specific to your particular motherboard. This will offer faster performance, but with a small decrease in stability relative to Expo 2. And finally, Expo Tweaked is an ASUS-specific overclocking profile that's tailored for your motherboard RAM kit combination. As a result, it will offer the highest performance boost, but at the expense of stability. So when I overclock my RAM, I typically start with Expo 1 and see if that's stable in Kahoo before trying out Expo Tweaked. If Expo Tweaked is stable, then that's typically the best option to use for max performance. What's truly fascinating is that if you look this up online, you will see a lot of misinformation, with Google AI incorrectly stating that Expo 1 is the most reliable option and that Expo 2 is more aggressive and could lead to instability. This is simply not true, and a good reason why you shouldn't trust AI tools when tuning your PC. For AM5 based Ryzen CPUs, there are 3 core clocks that you need to understand in order to learn how to optimize your memory subsystem. The best way to explain them is with a simple graphic, showing the key CPU elements and how they interact with each other. On the I/O die, there are a few core elements that are important to understand. The first is the Infinity Fabric, which runs at FCLK. This is how the CPU passes information from each core complex die, or CCD, to the unified memory controller. The memory controller runs at UCLK and is the component that connects the CCDs via the Infinity Fabric to the physical memory interface. The memory interface connects to the RAM DIMMs to pass information between the CPU and RAM, which runs at MCLK. So in order to extract max performance from an AM5 Ryzen based system, you need to optimize 3 core clocks. 1. The Unified Memory Controller or UCLK. 2. The Infinity Fabric Clock or FCLK. And 3. The Memory Clock or MCLK. To optimize the core clocks, you first need to select a RAM kit that your system will support. The memory speed that you're able to run stable will depend heavily on the quality of your motherboard, so you can use your Motherboard Qualified Vendor List or QVL to help guide you. However, as the memory speed increases, you will be forced to run the Unified Memory Controller at half the memory speed for your system. In BIOS, this is typically denoted by a UCLK mode option, which will show UCLK equal to MCLK or 1-to-1 mode, and UCLK equal to MCLK divided by 2 or 2-to-1 mode as choices. Some motherboards will automatically switch to 2-to-1 mode when you set your memory speed above 6,000 megatransfers per second. So if you buy a DDR5 6400 memory kit, I recommend setting this manually. It's also important to understand that the max UCLK that you'll be able to run stable will depend heavily on the quality of your CPU. The absolute maximum memory speed that you'll be able to run stable in 1-to-1 mode, if you get extremely lucky, is DDR5 6600, and this would be for a super golden sample. This is why memory manufacturers don't make 6600 Expo kits, because the chances of having it run stable are very low. Above 6600, you'll be forced to switch to 2-to-1 mode. However, speeds below about DDR5 7600 are not great options because your system will perform worse than simply running DDR5 6000 in 1-to-1 mode. So how do you select the best MCLK, UCLK, and FCLK combination? To help answer this question, I put together a table showing the Optimum FCLK for a range of DDR5 RAM kits. The second column shows the MCLK, which will be half the rated DDR5 speed since the RAM is double data rate. In 1-to-1 mode, shown in blue, the UCLK will be equal to the MCLK. However, in 2-to-1 mode, shown in red, the UCLK will be half the MCLK. In 1-to-1 mode, it's not possible to run the FCLK at the same speed as the UCLK, so unlike older AM4 based systems, this means your system will not be synchronized. You do, however, get a small benefit from running the FCLK at a 3:2 ratio, so an optimum FCLK for DDR5 6400 in 1-to-1 mode would be 2133 MHz. In 2-to-1 mode, it is possible to run the FCLK at the same speed as the UCLK, so as a result, your clocks can now be synchronized. That means that an optimum FCLK for DDR5 8400 in 2-to-1 mode would be 2100 MHz. As you can see, once you select your memory kit and mode, your MCLK and UCLK are essentially locked in. So the only real choice you're left with is what FCLK to run. Your system will typically perform better at higher FCLK values. However, you will run into stability issues if you push it too high, which is why aiming for some form of synchronization is typically a good idea, even if it's fractional. If you do, however, decide to push your FCLK as high as possible, a good rule of thumb is to push it until it no longer works and then back down 2 increments. Your FCLK should now be stable. In addition to selecting an Expo profile on FCLK, you should also consider adjusting your memory timings. You can watch someone like BuildZoid on Actually Hardcore Overclocking to learn how to do this manually, but most motherboards now come with automatic memory overclocking options that usually do a decent job. For ASUS motherboards, I typically don't spend time dialing in my sub-timings beyond selecting the Expo tweaked profile. However, I do try tightening my primary timings and increasing the DRAM refresh interval to 65535, which is a common tweak used by pros to help extract max performance from a system. For your primary timings, you can look for a similar kit of RAM to what you already have, but with tighter timings, to give you some ideas of what to try. For example, if you have a G-Skill Trident Z5 Neo DDR5 6032GB kit with primary timings of CL30, 38, 38, 96 at 1.35 volts, you can go to the G-Skill website where you'll discover that they also offer versions of this kit with tighter timings. You can then go into DRAM timing control in BIOS and manually dial in the tighter timings to see if they are stable. In this case, you would dial in a TCL of 26, since the other primary timings are the same. You will also need to set the DRAM VDD and VDD-Q voltages to 1.45 volts. You can then run a memory stability tool like Kahoo to check if your system is stable. If it's not, you can try adding some voltage. I would usually recommend trying increments of plus 0.01 volts to both VDD and VDD-Q. However, I wouldn't recommend going above 1.45 volts, so in this case it would be better to drop your voltage and try to match the CL28 kit instead. If you do decide to tweak your memory voltages, be extra careful to avoid anything larger than around 1.45 volts, since this could damage your system if used over a prolonged period. To show what type of performance improvements you should expect with these settings, I ran Cinebench R24 and 3D Mark CPU profile for a range of DDR5 RAM kit options. As can be seen in the table, the multi-core Cinebench score appears to increase linearly with MCLK regardless of latency, which would indicate that it's generally better to run higher frequency memory. However, the 3D Mark CPU profile scores don't show a similar linear trend, even though there does appear to be some benefit to running high-speed memory, even in 2:1 mode. It's also interesting to note that the power goes up significantly as you increase FCLK. For my kit of DDR5 8000 RAM, I was able to increase the speed to 8200 megatransfers per second and decrease the CAS latency down to 36. To synchronize UCLK with FCLK, you would need to set FCLK equal to 2050 MHz. However, most motherboards will not allow you to do that because they don't offer that option. The good news, at least for ASUS motherboards, is that leaving FCLK on auto will make the FCLK run at 2050 MHz. The best way to undervolt your AM5 based Ryzen CPU is in BIOS. When you enter BIOS on an ASUS ROG motherboard, click on the Advanced tab at the top. Scroll down and click on AMD Overclocking. Hit the Accept option when the warning pops up and then click on Precision Boost Overdrive. Precision Boost Overdrive is an AMD Ryzen CPU feature set, so it will be a selectable BIOS option from all motherboard manufacturers. In the Precision Boost Overdrive screen, click on the Precision Boost Overdrive drop-down menu and select the Advanced option. This will allow you to access multiple tuning options for your CPU, as explained later in the video. For this step, we're only concerned about undervolting the CPU, so scroll down and click on the Curve Optimizer option. Next to Curve Optimizer, the drop-down options are all cores, per core, and per CCD, which is an option for dual CCD chips like the 9950X and 9900X. I typically select the all cores option for single CCD CPUs and the per CCD option for dual CCD CPUs, because it takes considerably more time to dial in a per core undervolt, and the resulting performance increase tends to be small. Next to Curve Optimizer sign, select negative to indicate that you want to undervolt the CPU. Now you can input the magnitude of your undervolts for each CCD. For my 9950X3D, I was able to set the CCD 0's curve offset at -20 and the CCD 1 curve offset at -40. However, I would recommend starting at something lower, say -10 for each CCD, and progressing to higher negative values in smaller increments. Save your changes and reboot your system by clicking on Save Changes and Reset, and your undervolt will now be locked in. One thing to be aware of is that there are typically two ways to access Precision Boost Overdrive in BIOS. The first, which I just explained, is through the AMD Overclocking section. This is the option I recommend, and it should be available on all AM5 motherboards. For ASUS ROG AMD AM5 motherboards, the second is on the Extreme Tweaker screen. If you click on Precision Boost Overdrive, you will then be able to access a Curve Optimizer option directly. What's interesting is that you can set this in each location completely independently of the other, which is clearly not ideal. Once you boot back into Windows, you will now need to test the stability of your undervolt. You can do this with any CPU intensive workload, however, I've found that AIDA64 offers the fastest way to determine if you have a stable undervolt. After you open AIDA64 Extreme, click on System Stability Test at the top. In the System Stability Test screen that opens, make sure that there are tick marks next to Stress CPU, Stress FPU, Stress Cache, and Stress System Memory. You can leave Stress Local Disks and Stress GPUs unticked for the purpose of testing your undervolt. Click on Start and let the test run for around 10 minutes. If your undervolt is unstable, this test will rapidly terminate or your system will hang, usually within the first minute. If it does run successfully, then your undervolt should be good. Now you can go back into BIOS, dial in a lower curve offset, and rerun the stability test. When the AIDA64 system stability test errors out, simply go back into BIOS and re-enter the previous stable curve offset. Congratulations, you now have a stable undervolt. You can also undervolt your CPU directly in Windows using a free tool from AMD called Ryzen Master. I've experienced some issues using Ryzen Master in the past, so I would highly recommend making the changes directly in BIOS, but if you prefer to do it in Windows, then this is how you do it. Open Ryzen Master and click on Advanced View. Now click on Curve Optimizer on the left. Under Curve Optimizer Control, select the All Cores option. Under CO all-core value, you can type in a curve offset value. For the CPU shown in this example, it's set at -30. I would recommend starting at something lower, say -10, and progressing to higher negative CO values as mentioned earlier. Now hit apply at the bottom of the screen and a new screen will pop up asking you if you'd want to apply and test the offset values you just entered. Hit OK and your system will reboot to automatically make these changes in BIOS. Once it boots back into Windows, it will automatically load Ryzen Master and run a stress test. If the test completes successfully, you will see a statement in green at the bottom of the screen telling you. You should then test this curve offset to make sure that your CPU is indeed stable, as explained earlier in the video. You can easily check to see if your undervolt has been applied by loading Ryzen Master in Windows. After you load Ryzen Master, click on the Advanced View option along the bottom. If you look under Curve Optimizer Control, it should say CO All Cores next to CO Mode, and should have your curve offset next to CO All Core value. In this example, it shows a -30 curve offset. Regardless of which approach you use, as long as your undervolt has been applied, then it doesn't really matter how you got there. An important issue I came across during testing was something called clock stretching. Clock stretching is a safety feature that is built into all AMD Ryzen CPUs and can occur when you're too aggressive with your undervolt. When the CPU thinks the actual voltage is too low to sustain a stable system at a given frequency, it will reduce the clock period until the voltage is back at an acceptable level. So when you undervolt your CPU, you may think it's okay, but if you reduce the voltage too much, you will actually lose performance, even if your system appears to be stable. One way to check is to monitor your CPU clock speeds with a tool like HW Monitor or CapFrameX while your system is under heavy load. This is a snapshot of a stable 9800X3D CPU in Call of Duty Modern Warfare 3 with a -30 all-core curve offset. The CPU max clock frequency is 5425 MHz, which is what it should be for a CPU with a +200 MHz max CPU boost clock override. Whereas this is a snapshot of a different 9800X3D with the exact same -30 all-core curve offset applied. As you can see, the CPU max clock is reading 1250 MHz, which is significantly lower than what it should be. When I tested this CPU in AIDA64, it failed the system stability test within a few seconds of starting the test, even though I was able to run Cinebench and games without crashing. To prevent this from happening, all I had to do was back off slightly on the undervolt. Once you find a stable curve offset, you can rerun the benchmarks you used to baseline your CPU to see what the impact is. For my 9950X3D, a curve offset of -20 on CCD0 and -40 on CCD1 resulted in a small performance increase of around 2%. However, the CPU package temperatures dropped significantly, which is impressive. This decrease in temperature provides the thermal headroom that is required to overclock your CPU. Your results will vary based on silicon quality and cooling solution, but based on these results, it's definitely worth spending some time to find a stable undervolt. With your undervolt applied, you can now proceed to overclock your CPU. You can accomplish this many different ways, but for AMD Ryzen CPUs, the easiest way to do this is by using Performance Boost Overdrive or PBO. PBO is a feature set developed by AMD engineers to dynamically adjust power limits and clock speeds to boost performance. It's essentially an automated overclocking system that allows the CPU to run at higher clock speeds than its base frequency, provided there's enough thermal and power headroom available. Therefore, the quality of your cooling solution and motherboard will be vital in helping to determine just how much overclocking headroom you have. As explained earlier, to access PBO on an ASUS ROG motherboard, click on the Advanced tab at the top. Scroll down and click on AMD Overclocking. Hit the Accept option when the warning pops up and then click on Precision Boost Overdrive. In the Precision Boost Overdrive screen, click on the Precision Boost Overdrive drop-down menu and select the Advanced option. This will allow you to access multiple tuning options for your CPU. The first thing you should do is expand your default power limits. You can do this by changing the PBO limits option to motherboard, which significantly increases the power limits over default values. This will allow your CPU to run based on the power and current limits defined by your motherboard, which will allow you to take full advantage of your motherboard design. The only issue with doing this, however, is that your CPU package temps may go above 90 degrees Celsius under heavy load. So in order to keep your temperatures in check, I recommend also adding a platform thermal throttle limit. I typically recommend setting a thermal limit of 85 degrees Celsius for Ryzen CPUs. Depending on the quality of your cooling solution, this may reduce your performance slightly, but it will help prevent excessive and potentially damaging sustained boost behavior from occurring. To take full advantage of your motherboard's higher power and current limits, you should also consider increasing the max CPU boost clock. I've found boost clocks of around 100 to 200 MHz tend to work well for most chips. However, this is a tweak that is highly silicon dependent, so don't be surprised if you run into stability issues. This is a trial and error process. It's simple, but you need to be patient and take relatively small steps. I usually start by increasing the max CPU boost clock override in increments of plus 50 MHz. I then use Cinebench as the performance benchmark, combined with the AIDA64 stability test to check stability. Your objective is to find a peak in performance or a stability limit, which is the point at which your benchmark hangs or returns an error. When your benchmark returns an error or your score starts to decrease, you can back off to your last test point. When you are looking at data like this, it can be helpful to plot the data visually, so it becomes clear when you reach a peak in performance. Once you do find a peak or hit a stability limit, dial it in, hit save changes and reset, and this becomes your max CPU boost clock override. For my 9950X3D, I found that a boost clock increase of 150 MHz offered the best balance of performance and stability. There are a number of additional tweaks that you can make in Windows to help extract max performance from your system. The first is to go into Control Panel, click on Hardware and Sound, and then click on Power Options. For dual CCD CPUs, such as any Ryzen 9 chip, you should select the Balanced Power Plan. This will allow your second CCD to be parked while gaming, which will significantly boost your gaming performance. For Ryzen CPUs with only one CCD, such as Ryzen 7 and Ryzen 5 chips, you can select the High Performance Power Plan. There may be situations where selecting the balance plan is better, but overall the high performance option will result in higher average performance for single CCD CPUs. Another thing you can consider doing to boost gaming performance is turning off memory integrity. Memory integrity is a security feature in Windows 11 that helps prevent malicious code from being injected into core processors and ensures that drivers loaded onto your system are trustworthy. Unfortunately, it can significantly impact gaming performance, so while turning it off is not ideal, it's something to consider if you're looking to extract max performance in games. You can do this by going to Windows Security and selecting Device Security. Under Core Isolation, click on Core Isolation Details and make sure that memory integrity is turned off. Once you've finished making all of your tweaks, you should take some time to make sure that your system is in fact stable. But what does stable really mean? This can vary based on your needs. Some people think successfully booting into Windows is stable enough, but to me, stable simply means that your CPU will function without issue in the programs that you typically run. So the final tests that I recommend running to ensure stability are Kahoo to check the stability of your memory subsystem, and AIDA64 system stability test to check the stability of your Undervolt and Overclock. I typically run both of these tests for around 60 minutes each. You can of course choose to run these tests longer, but I've found that it's generally unnecessary for the vast majority of users. If you find that your system is unstable, then start backing off each tweak individually and retesting. This may take some time to get right, but the performance boost you achieve will make all of your efforts worthwhile. A bonus tip, and something I always do after tuning my PC, is to open a command prompt by typing in CMD in search, right-clicking on it and selecting Run as Administrator, and running the sfc/scan now command. This should find and repair any corrupt files on your PC that may have been generated during the overclocking process. Once you've established a stable overclock, you can rerun your benchmarks to see just how much of an impact the tweaks have on performance. For my AMD Ryzen 9 9950X3D, I was able to unlock max performance by making the following tweaks. 1. Set the PBO limits to motherboard. 2. Set the max CPU boost clock override to 150 MHz. 3. Set a platform thermal throttle limit of 85 degrees Celsius. 4. Undervolted with a negative per CCD curve offset. 5. Turned Expo on, set memory frequency to 8200 megatransfers per second, set CL to 36, and set refresh interval to 65535. And 6. Selected the balanced power plan and turned memory integrity off. The impact of these tweaks on performance is summarized in this table. I used Cinebench R24 multi-core as the benchmark, and I turned each tweak on individually so I could show its impact on performance, starting with the smallest and ending in the largest. When implemented together, the boost in performance is around 15%, with a decrease in latency of around 34%, which is exceptionally good. As you can see in the table, the largest increase in performance came from overclocking the memory, but the other tweaks made a significant contribution to the increase in performance as well. To see what impact these tweaks have on gaming performance, I selected 5 popular games and I compared the performance at stock settings against a fully tuned CPU. As you can see from Total War Warhammer 3, the average FPS performance increase is almost identical to the Cinebench results, with the 1% lows increasing even further. This isn't surprising when you look at the sensor data for this benchmark. which shows that the CPU max shred load is at 97%, while the GPU load is only at 74%. In fact, you can see similar performance results for all games that are CPU bound, with average increases of 6 and 14% in Cyberpunk 2077 and 10 and 47% in Microsoft Flight Simulator 2024. However, for games that remain GPU bound, even at lower resolutions and graphics settings, such as Call of Duty Black Ops 6, you see much lower increases in performance. This becomes even more obvious in Black Myth Wukong, which shows negligible increases in performance. If we look at the sensor data for this benchmark, it becomes clear that this game is heavily GPU bound, with the average GPU load at 94% versus a CPU max shred load at only 67%. This is why it's important to load CPUs when testing their relative performance. Your results will of course vary based on silicon quality, but based on these results, it's definitely worth spending some time to tune and optimize your system. Remember, it's not rocket science, it's Lego. My goal is to help you make the right component choices and put them together the right way every single time. Thank you for watching this video in the It's Not Rocket Science How-To series. If you enjoyed today's video, please hit the like button and subscribe so you don't miss out on future episodes. And if you'd like to support the channel further and gain access to some really great perks, please also consider joining our membership program. Bye for now.